Hello everyone. Today I will be introducing my term project, the 2D Truss finite element analysis, using a serial implementation in C++. The main goals of this project are to simulate a 2D truss structure made up of bar elements, to calculate nodal displacements, internal axial forces, stresses, strengths, and support reactions, and to export the results into CSV files for easier visualization and further analysis. The system takes two main types of input: node data, including coordinates, boundary constraints, and external loads; element data, including material properties, such as Young's modulus and cross-sectional area. This analysis focuses on a truss structure with 6 nodes and 9 elements. There are two types of support conditions. Node 0 is a pinned support, fixed in both x and y directions. Node 2 is a roller support, fixed only in y direction. External forces are applied at node 5. Apply a force of 50 kN to the left and 200 kN downwards. To compute geometric properties, first, the length of the element is calculated from node coordinates. Then, direction cosines are computed. Finally, element stiffness is calculated using the formula E times A divided by L. In this example, we apply 50 kN and 200 kN to node 5 in the x and y directions respectively. The code calculates the force vector using the global degree of freedom mapping. The table shows how each node's direction maps to the global force vector index. For each element, we calculate the direction cosines. Then, we construct the local stiffness matrix using a standard formula. Finally, we map the local matrix into global stiffness matrix. The formula on the slide shows the standard form of a 2D truss element stiffness matrix. We use Eigen's QR decomposition to solve the equation K.U equals F. Once solved, we obtain displacement value Ux and Uy for each node in meters. With the displacement vector U, we can compute the deformation of each element. Using this deformation, we calculate axial force, stress, and strength using the equations shown in the slide. The program exports node displacements and element results into CSV files, which can then be used for visualization, such as deformation diagrams and stress distributions. This flowchart summarizes the overall process. 1. Load nodes and element data. 2. Compute element properties. 3. Assemble the global stiffness matrix. 4. Apply loads and boundary conditions. 5. Solve the system and get displacements. 6. Compute reactions and others. 7. Export all results to CSV files. On the left is the result obtained by my friends from the structural group using their finite element analysis program, while on the right is the output from my own implementation. As you can see, the results are nearly identical, which verifies the accuracy of my program. This is my reference. Thank you for your attention.